Welcome back. So far, our discussion on quantization was mostly confined in uniform quantization. Yes, we have talked a bit about non-uniform quantization, but in this lecture, our discussion will be primarily focused on non-uniform quantization. Without any further ado, let's get started. In the non-uniform quantization, the quantization levels are not equally spaced. In the case of uniform quantization, the separation between consecutive quantization levels are always the same. There is no difference in this quantization step, whatever the quantization level is. But in the case of non-uniform quantization, we can see the quantization step is varied according to our need. Let's say in this example, on the left side we have a uniform quantizer, and on the right side we have a non-uniform quantizer, and both these quantizers are applied on same two signals, a strong signal and a weak signal. So in the case of uniform quantization, we have 0 to 15, total 16 levels, and the separation between consecutive levels are always same. You can see the separation between 0 and 1 level and the separation between the 1 and the 2 level are same. That means the quantization step is fixed all the way. But in the case of non-uniform quantization, the quantization step near the center is always very small, and as we go away from the center on either positive or negative side, our quantization step increases. You can see the middle quantization level, which is let's say in this case it can be 7. The gap between 6 and 7, or the gap between 7 and 8, these are very small gaps compared to the gap between, let's say, 14 to 15 or 0 to 1. So when we are near the center, our quantization step, or the gap between two consecutive quantization levels, is very small, but near the edge of the range, our quantization steps are very large. So we do it, and there is a certain significance or certain benefit of doing non-uniform quantization. Let me explain this. In most of the practical signals, for most time the signal is in low amplitude range, and for certain time period only the signal rises to a high amplitude. Let's say a human speech. A human speech exactly shows these characteristics. For the most time, signal amplitude is somewhere between low and mid range, and in some cases when we just press our voice, when we show anger or emotion, our speech signal jumps to a high amplitude. So that is not something usual. Usual is your amplitude will remain in small or medium range. Okay. So let's say this weak signal. We are using the same quantization schemes for both the strong and the weak signals. We have divided the whole range of the strong signal into 16 levels. We are not increasing or decreasing the number of levels for weak signal. So even though for this strong signal we have 16 levels to quantize, for the weak signal, in the case of uniform quantization, we only have 3 quantization levels. You can see 6, 7 and 8, or maybe 9. 4 quantization levels: 6, 7, 8 and 9. However, more quantization levels we have, like let's say 10, 11, 12, 13, 14, 15 or 0, 1, 2, 3, they do not affect or they do not come into any use for this weak signal. For this weak signal, we can only use these 4 quantization levels: 6, 7, 8 and 9. On the other hand, in the case of non-uniform quantization, one thing you should notice here, we are not increasing the quantization levels. We are not increasing the number of bits required. But this will perform better on weak signal, because in this case, for the weak signal, we are having quantization levels 5, 6, 7, 8, 9 and 10. So in total we have 1, 2, 3, 4, 5 and 6. So previously for the uniform quantization, for the weak signal we had 4 quantization levels. As we know, less quantization level means more error. But in the case of non-uniform quantization, we are having 6 quantization levels for this same weak signal, even though we are not increasing the number of bits. You can see the trade-off here. I have previously mentioned increasing the number of bit means great complexity, greater requirement of capacity. in this case, we are not increasing the number of bits. 16 levels means 4 bits. So in this case, both uniform and non-uniform quantization have 4 bits. So same complexity. But for the weak signal, you can see you have only 4 levels to quantize for uniform quantization, and you have 6 levels to quantize for non-uniform quantization. So obviously, non-uniform quantization will perform way better in the case of weak signals. But for the strong signal, they are more or less same. So if these strong and weak signals were not separate, they were in the same signal. Let's say you have a signal which actually varies a lot. In some time you have very small amplitudes, and in some time you have high amplitude. You have to incorporate the features of both these signals. If you use the same uniform quantization, that will not perform good on this type of signals. You want to have a non-uniform quantization. But if the signal is a simple sinusoidal wave or simple cause wave, in those cases where the amplitude levels are not varying much, in those cases you do not need any non-uniform quantization. Okay, so let's take an example of it. So let's say this is our signal. You can see in this signal, for most of the times, the amplitude level is very low. But for some separate times, let's say in this time the amplitude level is very high, in this time it is very high. So for most of the times the amplitude level is low, and for some time the amplitude level is very high. So if I want to quantize this signal, I have to have non-uniform quantization. Otherwise I will have poor results in the low amplitude region, and I will have a greater error. Okay. So we need non-uniform quantization, but we achieve it in a different way. We do not actually set our quantization levels in this way. It is not feasible. We do something different, and then we use this uniform quantization. So there are 2 steps basically. For achieving non-uniform quantization in this manner, it is not feasible because the quantization steps are varying. We use uniform quantization, but we do some operation before passing the signal to uniform quantization, so that these 2 operations in together actually performs like non-uniform quantization. So what is that operation? That operation is called compression. So when I will compress my signal and then feed it to my uniform quantization, this whole compression and uniform quantization will act together like non-uniform quantization. Let's see how it is done. So you can see here our original signal, then it is compressed, and then it is uniformly quantized. These 2 blocks together will act as a non-uniform quantizer. And in the receiver side, you get the reconstruction done, and then you do the expansion. These 2 blocks actually do the inverse of non-uniform quantization. You can say it non-uniform reconstruction. So in the transmitter side, you have to have a compression block before the uniform quantizer, and in the receiver side, you have to have an expansion block after the reconstruction. Okay, so in this case, we are introducing 2 new blocks. They are compression block in the transmitter side and the expansion block in the receiver side. These 2 operations all together is called companding. Compression plus expansion, or compression plus expanding, you can call it together a companding process. Okay, using non-uniform quantization, or using this style of compressing and then quantizing, we can achieve more SNR with fewer bits. Okay, more SNR with fewer bits. So let's see. So what is compression? I have talked about compression, that we need to compress the signal before passing it to the quantizer. So what is compression? Compression actually reduces the gap between the lower amplitude values and higher amplitude values. In this signal, you have a lot of lower amplitude values and some higher amplitude values. The gap is massive. This massive gap will result in very poor SNR when you will use uniform quantization. Okay, but if you compress the signal, then the total signal will be boosted somewhat, but the lower amplitude value will have a high boost, and the higher amplitude values will have a very low boost. In that fashion, you can see the lower amplitude values have gained some power, and you can see now the gap between the higher and lower amplitude values are very less compared to uncompressed input. So this is the compressor input, and this is the output. In the output, we have greater balance between the higher and lower amplitude values. As there is a good balance between high and low amplitude values, as I have said, the difference is not that much, we can now safely use uniform quantization without much problem. So after compressing, we will use the uniform quantization. So how we can compress a signal? So let's say mathematically how we can compress a signal. What's the equation? We can use two laws for compressing a signal. One is mu law and another one is A law. In North America, in Japan, and also for our purpose, mostly we will use mu law. So how can we use mu law? In the case of mu law, let's say x is our input and y is our output. One thing to remember, we are using this mu law after the sampling process. So at first we will sample the signal and then we will apply this mu law to each of these samples. In our previous example, we have said that we were given a sequence and then we used a quantizer to quantize that sequence, quantize each of those samples. We will be given a sequence of samples. We will not directly feed the samples into the quantizer. In a similar manner, we will design a quantizer, but before feeding a sample to the quantizer, we will pass the sample through this mu law or through this equation. The x is the input and y is the output. Okay. So let's see, y is equal to y max. Then we have a fraction here. On the numerator, there are ln. E-based log is ln of 1 plus mu multiplied by absolute value of x by x max divided by ln of 1 plus mu, and the whole thing is again multiplied by SGN or signum of x. You already noticed signum from your FM lessons. Signum is basically the sign of the signal. If the signal is positive or if the sample is positive, SGN x is plus 1. If the sample is negative, let's say minus 5, then your SGN x is minus 1. X max is the highest value of the signal. Typically, this x max and y max are same. So one thing to note down here, that is x max and y max are same. So if your x max is 10, by default your y max is 10. Then mu is basically the constant of this mu law, and mostly mu is 255. Note this value down also, mu is 255. If any other mu is explicitly mentioned in the question, you have to use that mu. But if no mu is mentioned, then you can safely use mu equal to 255. So we know all these values here. All these sequences will have a x value or an input value. Let's say if your sample is 5, then the x is 5. And you have a x max from the input signal. The maximum value of the signal is x max. Or in some cases, the maximum value of the quantizer is x max, depending on the question. So if you have the x, you have x max, you have mu, you have y max, so you can easily determine the value of y. So let's say I have 5 samples. For each of the 5 samples, I will need to do this operation for compression. We will see a mathematical example in our live class. So here you can see the compression characteristics. You can see as my mu is increasing, the graph is shifting in this direction. So when my mu is 0, that means no compression is used. So all the input and the output have the same value. You can see in this graph, if your input is 0.2, your output is also 0.2. So no compression or no boost actually. But when you are using a mu of 255, you can see when your input value is 0.2, your output value is, let's say, 0.65. So it is a great boost. But when your input is 0.8, your output is 0.9. So you can see this mu law or this compression technique is giving a larger boost to lower input values and a very smaller boost to higher input values. That is how we are compressing the input signal. There is another law, that is A law. Basically the same thing, except A law is used in Europe. There are 2 parts in A law, basically the similar as mu law. I advise you to take a look at this. I am not explaining this because these are the similar as mu law. If A is 87.6, then using A law and mu law are basically the similar. We are not going to use A law in our discussion, just you have to know about it. There is another law, A law, which is used in Europe. We will use mu law in our case. So we are done with quantization. So for non-uniform quantization, we have to first compress the signal and then quantize it. Now finally encoding. So how do we encode our signal? Let's say we are using 4-bit encoding. 4-bit encoding means 16 quantization levels, 2 to the power 4 equal to 16. So we number them as 0 to 15, and we have a 4-bit binary number for each of these levels. Let's say 0 level is encoded as 0000, 1 is encoded as 0001. In this fashion, the 15 is encoded as 1111. Obviously, you should get an idea where we are getting these binary numbers. We are using 4-bit quantization, right? So each of our level will be encoded with a 4-bit binary. If we were using 5-bit binary, then each of our quantization levels would be encoded as 5-bit binary. If we were using only 2-bit binary, then each of our quantization level would be encoded as 2 bits, 00, 01, 10, and 1. How this encoding is done? Let's get back to our previous example. We have already done this example. There are 4 quantization levels, you can see. So obviously this is a 2-bit encoding process. In 2-bit encoding process, we use 2-bit to represent each level. Let's say this is our first level. So this is 0th level, and its corresponding binary encoding is 00. This is 01, this is 10, and this is 11. So our first sample is quantized as 1.125, which is the 4th level, and we will encode it as 11. The next sample is quantized as minus 0.375. Minus 0.375 is our second level, and we will encode it as 01. So 1101, another 01. Then we have this level, which is 10. So 11, 01, 01, 10, 11, and 11. This whole thing is our digital sequence. So we are done with our PCM system. We have talked about each of these components in great detail. Moving on, we need to use some line coding schemes. We have to use this line coding in our digital modulation in our next lesson. So even if this line coding technique is in this slide, but I will talk about this line coding technique in our next lecture. So this is the end of our PCM or pulse code modulation. Hope to see you in our next lecture in digital modulation. Thank you.